Welcome to an exciting segment. This is the last section in Chapter 6, Section 6.4, first segment here. So just a quick sort of discussion. So far, the equations that we've been looking at, the trigonometric equations, have only involved the forward functions, sine, cosine, tangent, whatever. But we have yet to look at equations that may involve inverse trig functions. And so that's kind of the meat of what's in section 6.4. But there's also this sort of weird group of problems that appears at the beginning that I don't want to spend a whole lot of time on, but maybe I can run through a couple of them so you can sort of see them and recognize them as you do the homework. There's not a whole lot there, but let's take a look at them. So let me just shift over here a second. I've got to plug in properly. Okay, so this is section 6.4, page number 1. I think that pen has had it. Okay, so let's look at this sort of problem. And I've got a couple of them. I don't know how many we'll actually do, but so we want to solve for x in terms of y. And here's an example problem. Y equal to 4 tangent of 3x. Now, and then it also has this qualifier that says that x is somewhere in the interval negative pi over 6 to pi over 6. Now, you may be looking at that going, well, that must be really important information. And unfortunately, it's really not. It could be the case that they could be asking you to do some sort of unusual kind of thing. But basically what this is saying is that the tactic we're going to use is to take the inverse tangent of both sides of these equations. And you recall there were issues with if you're taking the inverse tangent of a tangent and the argument isn't in the right range, and you end up with screwball things coming up. So basically every one of these problems give this kind of thing, but they don't do anything interesting with it. I mean, you could certainly say, well, what if x is between pi over 6 and say 3 pi and pi over 2? That would be another possible group. But this is basically a single period of the tangent function. And that's where that's coming from. Single period of the tangent function. It happens to coincide with the values that inverse tangent will produce. And every one of these problems does that. I don't know why they even bother with this if they hadn't given at least one that is something different. But that makes these, because they're because they don't have those issues, these problems are actually relatively trivial. So the first thing that we would do when we're trying to solve for x in terms of y, that means we need x by itself, x equals something in terms of y, maybe some functions or that or whatever else. We should have that at the end. So the first thing I would do is to divide both sides by 4. So we have y over 4. And then the most likely thing to do is to take the inverse tangent of both sides of this equation. Now this is where that issue comes in, right? So inverse tangent of 3x. And if you recall from section, and we have inverse tangent of y over 4. So as you recall in that section 1, we talked about taking inverse trig functions of trig functions. You have to make sure that the argument is in the range of the inverse function. Otherwise, there's some kind of a difference. Well, if you look at if x is between negative pi over 6 and pi over 6, then 3x happens to be between negative pi over 2 and pi over 2, which guarantees that this argument is in fact in the range of the inverse tangent function. So these these two functions in some sense cancel each other out. And what you're left with is 3x is equal to the inverse tangent of y over 4. So x must be equal to 1/3 times the inverse tangent of y over 4. And that right there is the answer that they're looking for. So as I said, every one of these problems, they're almost too easy because they don't do anything with that. But here's another example. Let's take, how about y equal to 3 sine of x over 2, where x is between negative pi and pi. And just to kind of get your bearings here, notice x is between negative pi and pi. That means x over 2 is actually between negative pi over 2 and positive pi over 2, which happens to be the range of the inverse sine function. So you can kind of see this is not really doing anything special there. So same as before, we take, we divide by the leading coefficient. So we have y over 3. Then we take the inverse sine of both sides. So we have the inverse sine of the sine of x over 2 is equal to the inverse sine of y over 3. Again, we have to be careful with that, but it turns out that the argument x over 2 will always be within the range of the inverse sine function. So these two functions unzip themselves. We have x over 2 equal to the inverse sine of y over 3. And so consequently, x is equal to 2 times the inverse sine of y over 3. Not terribly exciting and not a whole lot different than the previous problem. So let's see. I can try a couple more. I mean, it's not really a big deal. They're quick and easy. So let's consider and to be honest, this is the kind of stuff you may actually do a lot of, this kind of manipulation back and forth using signs and using functions and their inverses. So maybe it's not totally wasted practice. So y equal to 4 plus 3 cosine of, I think this one's just simple, x, where x is between 0 and pi. Notice that is the range of the inverse cosine function, conveniently. So we'll subtract 4 from both sides, then divide by 3, kind of switching sides from one line to the next, but it's not totally uncommon. And then we want to take the inverse cosine of both sides. So we've got inverse cosine of x equal to inverse cosine of y minus 4 over 3. And of course, as the argument we've already made, x is in the range of the inverse cosine function, so these functions kind of wipe each other out. So we have x is equal to the inverse cosine of y minus 4 over 3. I've got one more, and like I said, it's not challenging to do. So I'm going to go ahead. The range is a little bit, the values of x are a little bit weird on this one, but it's not really a harder problem. So let's take y equal to tangent of 2x minus 1. And here they say that x will be between 1/2 minus pi over 4 and 1/2 plus pi over 4, not inclusive. So this is kind of the thing where you have to convince yourself, if I have x values in here, what will be the range, or what will be the possible values of 2x minus 1? Well, if you needed to do this, you'd come over here and say, all right, well, if this is the values that x falls between, then 2x must fall between 1 minus pi over 2 and 1 plus pi over 2. So 2x minus 1 must fall between negative pi over 2 and pi over 2, which just happens to be the range of the inverse tangent function. So that's, again, it looks a little different, but it's the same basic result. So this problem reduces to taking the inverse tangent of both sides. Kind of running out of space here. So to inverse tangent of 2 minus x equal to inverse tangent of y. The left-hand side, because we've already verified that 2x minus 1 is always in the range of the inverse tangent function. Again, we have this just sort of cancellation of those two functions. So 2x minus 1 is equal to the inverse tangent of y. And so now our challenge is just to isolate x. So 2x equals 1 plus inverse tangent of y. Divide both sides by 2. We get that x is equal to 1/2 plus 1/2 times inverse tangent of y. So these are some relatively easy kinds of problems that appear at the beginning of section 6.4. They're not terribly exciting, but like I said, they are the kind of thing that you might actually see in a physics class or other places where you're trying to do these applications where you've got some kind of an equation involving a simple trig function, and you might want to find the other variable. So as a formula, not just as a number. So interesting. This is the first example of where we've had two variables in an equation. Well, aside from graphing, there we go. I think there used to be some parts in this chapter that involved the graphs of inverse trig functions, but I finally just took them out because there really wasn't time to teach the material effectively. And it's the kind of thing that, I might add, there might be one question in there that is designed to make you think about how these inverse functions are graphed, because it turns out that there's some really cool relationships between the slope of those graphs and rational numbers or rational functions that you see at the end of a Calc 1 class. Anyways, I don't want to get too long-winded here. I will see you in the next video. We may only have one more video, but I don't know, some of these actual inverse trig equations take a little bit of time, so we'll just see how we do.